But we have an exciting day ahead, and we start with an overview talk by Shlomo Razamat on recent developments in formal SQFT, a duality perspective. Thank you.
So first I would like to thank the organizers for organizing this really amazing meeting and really amazing party yesterday. And again, I thank you all for waking up today. So I will be talking about some recent developments in understanding formal SQFTs from a very particular perspective. So I was given this task to review formal QFT. Formal QFT is an amazingly rich subject. Like if you ask different people, you will come with different answers what formal QFT is. So, but in general, I think most people will agree that this is a research driven by theoretical laboratories, some toy models exhibiting some non-trivial effects with various motivations depending on different people, computability and strong coupling, some envisioned applications, and maybe interplay between these different motivations. So my motivation will be to understand physics beyond these strong coupling barriers. So the way we usually think about QFT, we start with some theory, which we understand in some way, and then we deform it, and either with some continuous parameter, it can be an exactly marginal coupling, or relevant deformation which triggers a flow, and then we want to understand what happens in the infrared, and typically the interesting physics happens when the theory in the infrared is separated from the theory in the UV by some strong coupling regime that we don't understand. So we will discuss toy models providing us with enough tools so that we will be able to understand physics beyond this strong coupling barrier. So what are these tools? So tools which exist basically for any theories are symmetries and anomalies. And these concepts in physics are amazingly generalized in recent years. So you can try to understand symmetries and anomalies on one side, and this will tell you something about these objects on the other side. If you have supersymmetry, you have many more objects that you can compute here, which will tell you about the physics on the other side. These typically take a form of some type of partition function. And all of these things are some kind of counting problems. You can count something on this side, and this counting will tell you something about the physics on the other side. So in this talk, I will only discuss toy models with supersymmetry because I have these additional tools that I can discuss to understand physics on the other side. Now, we will not only try to understand physics on the other side, we will center our discussion about something which is called a duality. A duality is a concept when you have a certain theory which can be reached by different by deformations of different theories, by, say, relevant deformations of different theories. This goes under the name of IR duality. So you start with different theories in the UV, you turn on some deformation and you flow to the same theory in the infrared. Or there is a concept of a conformal duality, when two theories are connected by exactly marginal deformations without breaking conformal symmetries. So dualities turn out to be a very rich theoretical laboratory, and that is the reason why I will center the discussion around dualities. Many of the developments in formal QFT in recent years are directly or indirectly related to dualities, and this is also subjectively the way that I like to present or think about the subject. So this how our discussion will proceed. So we'll organize the discussion around the notion of duality, and the motivation will be understanding better QFT constructions. All possible QFT constructions are renormalization group flows, some mathematical physics related to dualities, and dualities that we can infer from mathematical physics. Now, the discussion will be centered also on examples. I will not, it's very hard to give some very, very generic pictures, so I will give various examples which will exemplify various interesting research directions that people consider. So let me start with some trivial examples that all of us should know from around 30 years ago. So the basic example of infrared duality is what is called Seiberg duality in 4 dimensions, where you have, say, an SUN-C gauge group with some matter, fundamental and anti-fundamental matter, which flows in the infrared to the same theory as another gauge theory with another gauge group and similar matter, but not exactly the same matter and some superpotential. There are many examples of such dualities that were accumulated in the 90s. For example, there is this also famous interligator-Puyo duality, where instead of SUN group, you have USP to NC groups. So double circles will denote in this talk USP groups and single circles SUN groups. Again, it's very similar duality. You have two different gauge theories which flow to the same fixed point. You can discuss duality in other dimensions. For example, there is a similar duality in 3 dimensions, where instead of SUN groups, you have UNC groups. And in 3 dimensions, you have additional things that you can do. And the duality works in such a way that the superpotential that you need to turn on for this duality to work involves monopole operators. So there are a lot of examples that one can consider. So also, let me remind you some basic examples of conformal duality. So the canonical example, the spherical cow, for the people in this audience, I think, is the n=4 super Yang-Mills. And it is a canonical example of a conformal duality where you have an exactly marginal coupling, which is the gauge coupling. You can tune it preserving n=4 supersymmetry, and then at strong coupling, another description emerges with almost the same gauge group. So in the case that the gauge group here is SUN, there is a dual description with the group SUN mod Zn. For some groups, there are also additional exactly marginal deformations that you can turn on, which preserve only n=1 supersymmetry. Another important example of a duality that people have studied is what is called Argyres-Seiberg duality, where you start with n=2 gauge theory, say SU3 and F=6 SQCD. Again, you tune its exactly marginal gauge coupling, and at some point on the conformal manifold, in the space of exactly marginal couplings, another description emerges in terms of some funny, strongly coupled SCFT with additional free matter, and you gauge some global symmetry of this combination of theories. Okay, so there are a lot of examples of these strongly coupled SCFT. So the strongly coupled SCFT that appeared on the previous slide will be also an important player in the game that we will discuss. So actually most of the theories, of the conformal theories that we can consider are strongly coupled, are intrinsically strongly coupled. That is true about CFTs in 6 dimensions and in 5 dimensions. Also CFTs in 4 dimensions. We can start with weakly coupled Lagrangians, but we can flow to strongly coupled CFTs. This is true for the Seiberg theories that we discussed in certain regime of parameters, at least. There are these Argyres-Douglas theories, funny theories that people discovered in the 90s, Minahan-Meshansky theories. 3D gauge theories also typically flow to interacting as CFTs. So there is a zoo of theories that we can consider in different dimensions, and there is a zoo of relations between these theories that people have discussed in the past. Now, sometimes people call some of these theories non-Lagrangian theories. I hate this name, so this is a time-dependent name. It just means that we don't know a Lagrangian for a given theory. We don't know of some description of a theory, of a given theory, like of a given CFT which flows to it. But with time, we find more and more Lagrangians for more and more theories, so I will not use this name. Okay, it's not something we should consider. Okay, so this is the situation. We have many scattered instances of CFTs and dualities relating them. We have a lot of evidence about existence of interesting CFTs in higher dimensions like 6D and 5D, where field theoretic constructions are not available. And what we will ask is whether there are any schemes, any ways of thinking which will help us organize this zoo of observations. Okay, or in other words, is there a structure to the space of all supersymmetric conformal field theories and RG flows interconnecting them? So we will discuss very, very briefly, again, based on examples, 3 schemes: a geometric scheme, a reductionist scheme, and what I will call a big data scheme. Okay, and all of these things are related. I also will make some comments about relations of some subjects in math to the discussion of supersymmetric conformal field theories. Again, it's not an exhaustive review. It is my personal take on the subject based on some examples. but we will touch on different interesting aspects of the developments. And I will try to cite many papers, but the subject is huge, so I will certainly not cite all the papers, and I ask for forgiveness for people who will not appear on the slides. It's not because the work is not important, it's because for other reasons. Okay, so let us start with the geometric scheme. Okay, so what is a geometric scheme? So implicitly in what we have discussed and the way we thought about dualities in the 90s, we would consider all the theories in this diagram to sit in the same number of space-time dimensions. So Seiberg duality, we have two theories in 4 dimensions which flow to a theory in 4 dimensions. But it turns out that it is much better to consider relations between theories which do not necessarily live in the same number of dimensions. We can start with 2 theories living in different dimensions, not necessarily in the same dimensions, and end up with a theory which lives yet in another number of dimensionality. When we connect theories in different dimensions, we do something with geometry, okay? So we can understand this flow across dimensions with some kind of a geometric structure. And understanding this geometric structure gives us an additional tool to kind of order and understand the set of all dualities, all CFTs and all dualities that one can consider. So I will give you an example of such an across-dimension duality. So for example, we can start in 6 dimensions with some 6-dimensional 1,0 theory, which is called rank 1 E-string theory. We can deform it geometrically by putting it on a compact space on a genus G surface and go to low energy. At low energy, we effectively will arrive at some 4-dimensional QFT, and in this case, it will be a CFT. One can come up with a claim that says that there is a 4-dimensional theory, so you start in another number of dimensions, in 4 dimensions, with some complicated gauge theory, you deform it in a certain way, and you flow to the same fixed point in the infrared. How do you check these dualities? You check these dualities with tools that I mentioned. You compute anomalies, symmetries, partition functions, and so on. I will not have time to give details, but you just compute the same things like Seiberg computed in the 90s. It's the same thing, anomalies, deformations, partition functions, which are relatively new tools, but you match all of this, and then you conjecture this duality. It's always a conjecture, okay? In this particular case, you can actually describe this CFT directly. There is a conformal theory. This is a conformal theory, meaning there is no flow, like an equals form. You can turn on coupling such that the beta function will be exactly 0. There are exactly marginal parameters which describe this CFT exactly, so you have here a duality directly in 4 dimensions, in the sense that you have a description of a conformal manifold using this theory, and there is some theory flowing to this conformal manifold. Now, if you really squint hard and look at these quivers, you can see a geometry, this kind of a Riemann surface sitting inside this, in this gauge theory, so this quiver theory description of these theories. You can think of this theory as kind of two vertices with G plus 1 legs, which you glue together. And here you can view it as 2G minus 2 trivalent vertices that you glue in such a pattern to form this quiver. So these are the vertices, you glue them together and you get such a surface. So there is a hint that you can view these 2 theories using this geometry, okay? And in fact, in this case, it's more than a hint. You can really understand these 2 different theories as gluing of some basic building blocks in 2 different ways to form such a geometry and then to produce a theory that you obtain in such a compactification. So there is a complicated duality here that you can understand in a geometric way, and this is how, in general, this geometrical scheme works of understanding dualities. You start from some complicated theory in higher dimensions. You have different ways of cutting the geometry. Okay, for example, you can cut it in such a way, or you can cut it in such a way. All these different ways, because of magic of supersymmetry, should be equivalent. you understand what are the reduction of the building blocks to lower number of dimensions, and in the example we have here, this is reduction to 4 dimensions. Then you understand what this geometric operation of gluing together surfaces means in the field theoretic language, and typically it means gauging certain symmetries and turning on superpotentials. And then these two different ways of cutting the surface will produce two different Lagrangian descriptions, or two different 4-dimensional, lower dimensional descriptions in more generality of the same theory, and that is how you can derive a duality. And by now we have an amazing plethora of dualities that can be derived like that. In particular, the vanilla Seiberg duality can be derived in certain setups of this form. So let me say several words about like the important ingredients of what you need to understand to proceed with this geometric scheme. So the important thing that appears here is to understand how to cut surfaces. Okay, so how do you cut surfaces? So geometrically, you can think of cutting a surface. Say you compactify on a 2-dimensional Riemann surface. So you look on a tube, and the tube can be thought of as circle compactification of your d-dimensional theory, and then you cut it, and the cutting means that you introduce a boundary or a type of a puncture. So you need to understand boundary conditions in the circle compactifications of your d-dimensional theory. Now, typically, or in many cases, I would not say typically, this circle reduction of many theories, even higher dimensional theories, 6-dimensional theories, can be described by a gauge theory. Okay? And the canonical example, if you take a 2,0 in 6 dimensions, you compactify it on a circle, you get a maximally supersymmetric Yang-Mills. These theories in 5 dimensions, in this case, are not UV complete in 5 dimensions. They are UV completed by the theories in 6 dimensions. Okay? And here is another example. So what happens in these cases, you compactify on a circle, you get an effective description in terms of fields, in terms of gauge fields, and you can study the boundary conditions that you can impose on these fields when you cut the surface. And this involves understanding to which fields you need to give, for example, Dirichlet and Neumann boundary conditions, and usually you want to preserve some supersymmetry in this business, so you come up with certain boundary conditions. And the example that I gave you before is a special case of such a construction. For example, the E-string is a special case of these 6-dimensional CFTs when you take n to be equal 1. So the basic kind of an ingredient that you can derive is that if you compactify on a sphere with 3 punctures with certain geometric information, additional geometric background fields turned on, you get a theory of this sort, a very simple quantum field theory with SU2n plus 1 gauge group with some fields in antisymmetric representation, fundamental and anti-fundamental representation. And what is associated to the punctures is a global symmetry which comes from the gauge symmetry in 5 dimensions. So when you put these boundary conditions, for example, you typically freeze the gauge degrees of freedom at the boundaries, and then this gives rise to additional gauge symmetries, global symmetries in lower number of dimensions. And to glue things together, you need to undo this operation of cutting and freezing degrees of freedom, which will be just reintroducing some additional fields and gauging these symmetries associated to the punctures. So this is the name of the game with which you can play. And again, these type of theories are exactly the building blocks that you can use to derive the duality example of which we gave before. So let me give several comments about the punctures. So these boundary conditions, which are a very important part of this story. So even in the case of 2,0, which is the most studied example of this compactification, and as you can see, I did not emphasize the 2,0 story. The story that I'm presenting here is true for any 1,0. 2,0 will not play any role, although 2,0 is the case which was studied the most. A lot of punctures preserving n equal 2 supersymmetry were studied in the literature, and we understand them very well. So this involves understanding various types of boundary conditions. However, there is also, there should be also a much richer zoo of punctures which will preserve less supersymmetry, and these were much less studied. So there are works, so this is very, very partial list of papers related to these works, and there are conjectures that relate the recent constructions of spindles also to these new types of punctures in 2,0 theories. Now, in the discussion that we had till now, I told you that in many cases, when you take, say, a 6-dimensional theory and compactify it on a circle, you get a gauge theory description. But it doesn't have to be true. In some cases, an effective description that you get in 5 dimensions is some field theory in 5 dimensions, which is UV completed in 6 dimensions, but it doesn't have to be a gauge theory. Okay? For example, it can be some strongly coupled 5D SQFT with some of its global symmetry gauge, so that it is not UV completed in 5D, but in 6 dimensions. And this story was completely not researched till now. There is only a single example of such a construction when you use this way of cutting the surface, understanding a 5-dimensional theory, and deriving 4-dimensional dualities using this way. So this is a big open problem in the field, in the field of this compactification. And here is an example why it is important to understand all the possible ways to cut surfaces. So we discussed like different pairs of Pence decompositions, which give you a duality. And here is a simpler example when you have a torus compactification on some theory, and you can cut this torus into 2 tubes and glue them together in different ways. And these different ways correspond to different 5D descriptions that you will obtain while cutting. So in one case, you will get this theory very systematically. In another, you will get this theory, and different colors and shapes correspond to different groups. These 2 theories look extremely different. There are some patterns, but they look very, very different. Nevertheless, they are conjectured to be exactly dual to each other. Okay, and one can check the protected information, anomalies, and the partition function and convince themselves that they agree. Another interesting notion that is to start from 2 different theories in 6 dimensions and put them, deform them differently by placing them on different geometries, and in some cases you will get the same theory in 4 dimensions. Okay, so you can think of it as a 6-dimensional duality. You take 2 different theories in 6 dimensions, do to them different things, and get the same thing in 4 dimensions. There is a zoo of examples of these types of dualities, but we don't understand them systematically. Okay? The situation with many four-dimensional dualities, when you have dualities in 4 dimensions that you can engineer starting from 6 dimensions, there is some geometric understanding, but here kind of we push the starting point to the highest number of dimensions. We can come up with a lot of examples, but we don't understand the pattern. So I would say that the situation here is as the situation was 30 years ago with Seiberg duality. We have a lot of examples, but we don't understand the pattern. One can ask many other interesting questions. For example, can one derive all possible 4-dimensional QFTs or SQFTs using this geometric setup? And we don't have an answer. There are many theories for which we don't know such a geometric construction. But here is an example of, I think, the weirdest 4-dimensional theory, which was missed in many compactifications in the past. You take an n=2 theory with USP4 gauge group, and it has a single half hypermultiplet in 16-dimensional representation. So it's a very weird theory. Nevertheless, it is a perfectly good theory, and only recently, very recently, it was realized by some compactification starting from 6 dimensions, and there are many other examples of relatively funny theories that you can engineer starting in 6 dimensions. So there is nothing sacred in 6 dimensions. You can perform these operations in other dimensions. For example, you can start from 5 dimensions and go down to 3 dimensions. Odd dimensions are bad because we lose some tools to address our theories. For example, we don't have the tool of continuous anomalies for continuous symmetries. So it's much harder to test dualities, but nevertheless, you can do this by studying emergence of symmetry that you expect from 4-dimensional theory, studying discrete symmetries and so on. And here is an example of a duality recently derived. In 3 dimensions, the field theories are richer. Maybe 3 dimensions is the richest setup for studying quantum field theories. For example, you have Chern-Simons levels that you can turn on for various groups, and monopole superpotentials that I have already mentioned. Now, although the way I present it, again, based on examples, we have, it doesn't seem that there is some structure, but nevertheless, there is an algorithm that one can come up with to derive such cross-dimensional dualities, at least in some cases. So one can systematically understand compactifications on tubes, say, on a circle to 5 dimensions, then put boundary conditions and try to understand what compactification on a circle times a line gives you in 4 dimensions, and understand flows between 6-dimensional theories and interplay between turning on background fields when you compactify the fluxes for global symmetries and punctures to derive a certain algorithm to derive general cross-dimensional dualities. I don't have time to give you any details of this. So this is a summary of this geometric scheme. So using this geometrical scheme, we can partially systematize understanding of a lot of scattered SQFT results, such as dualities and emergence of symmetry. We can systematically construct new examples of dualities, okay, dualities that were in principle not known before. To understand such a cross-dimensional dualities, we need to integrate together a lot of understandings about the different CFTs. For example, classification of 6D CFTs, their compactifications to 5D, relations between them, and many other things. Generalized symmetries only start to enter this discussion. So there is a lot of work done done by many people, but also by many people in Oxford in particular, on trying to understand symmetries in these compactifications using geometry, but still, like in trying to map or understand these symmetries directly in quantum field theory constructions such as Lagrangian, only few works exist at the moment, and there is a lot to be done. And there is this important question that we can ask, whether we can understand all SQFTs as some kind of geometric constructions. So let me now go to a second scheme, the reductionism scheme, and this scheme is related to the geometric scheme. So what was basic idea of the geometric scheme? We wanted to understand some effect in quantum field theory, and the way we understood it, we complicated the problem. We started in 6 dimensions, and 6-dimensional theories are very complicated. And then we viewed the 6-dimensional theory in different ways, or compactification of this 6-dimensional theory in different ways, and we understood some dualities. But there are many other ways to do the same procedure. We can understand different theories here as fixed point, as the infrared fixed points of renormalization group flow, starting from some very complicated theory. And then if this is the case, then again the same type of an argument can be made for a duality between these two theories. So, but the real question is, what is this magic theory from which the two theories which are putatively dual to each other follow? Okay? So a geometric construction is one example of that, but there are other things that one can do. For example, one way to complicated things was already discussed a lot of years ago. This goes often by the name of Berkus-de confinement. So if you have a gauge theory, you have gauge groups and you have matter fields, but in some cases, using some known dualities, you can turn matter fields into gauge theories. Okay, in some cases, gauge theories flow in infrared to some collections of matter fields. So if you have a certain gauge theory with some matter, you can exchange this matter with some gauge theories. You construct a more complicated theory, and you can use some field theoretic information such as duality on these complicated theories to derive other types of dualities. And here is an example. This is a weird duality that was conjectured again long time ago by Chucky, Schmaltz, and Skiba. You have weird matter content. It was conjectured that this theory flows to some West Zumino model, and using this type of arguments, this duality was proven recently to follow from very basic interligator-Puyo and Seiberg dualities that we have discussed before. So a question here is whether there is a basic set of QFT dualities from which all the other dualities follow. So I have shown to you some dualities which look complicated, but are they interesting at all? Does everything follow from Seiberg and interligator-Puyo, or maybe some larger set of dualities? Okay. So here is another example. here is a conformal triality. So all of these theories are conformal, they don't flow, and one can argue that they are dual to each other. And you can actually show that they are dual to each other by starting from this most complicated description of the theory, performing some basic duality on one of the nodes, and showing that you get this theory. So although this triality was conjectured because of some other reasons. So let me mention here a certain relation to mass, which is very useful, and it will lead to some interesting conclusions. So cyber duality was something which was discovered in 1995. Later on, there was defined a certain object which is called a superconformal index. And this index doesn't depend on continuous parameters. So if you have a dual pair, the index should agree for two dual theories. You can compute the index, and it implies certain identity of complicated special functions. Amazingly, a mathematician, or sequence of mathematicians starting with Spiridonov and ending with Eric Reins, have conjectured exactly these identities 2 years before the computation was defined. So the index was discovered in 2005, but this identity was derived in 2003 without any reference to cyber duality. He didn't know that he proves index identities for cyber duality. I don't understand motivations of mathematicians, but he had some good motivations, okay, to derive such a duality. So once we understand that there is this interesting relation between complicated physical statements and complicated mathematical physics, complicated mathematical results, we can start reading actually mathematical papers of different kinds. So for example, since we know that Eric Reins can produce some physical results without actually studying physics, it's worth reading his papers. And if you read this particular paper, for example, you derive a very interesting result, which was thoroughly explored by Sara Pasquetti and collaborators. So there is this very interesting phenomenon in lower dimensions of 3D mirror symmetry. But what actually follows from the study of Eric Reins of certain special functions, that you can understand these 3D mirror symmetries as four-dimensional, as following from some four-dimensional infrared dualities, which in turn you can just understand as interligator Puyo and cyber duality. So a lot of seemingly unrelated three-dimensional dualities are related to interligator Puyo and cyber, and it is hard to guess this thing if you just do physics because of the following reason. So the theory that, in physical language, the theory that Reins has constructed is this monstrosity. Okay, it has a lot of symplectic groups with a lot of fields of different types, and the mathematical claims of Reins are equivalent to stating that the flavor symmetry of this theory has an USP2n times USP2n flavor symmetry group, although in the UV, in the Lagrangian, you only see USP2n times SU2 to the n global symmetry. But again, study of the index indicates that there is such an enhancement, and then using various techniques that we have mentioned, and dimensional reduction, you can show that what follows from this statement is a statement about many mirror symmetries. This is a canonical example of mirror symmetry in 3 dimensions discussed by Gayotto and Witten many years ago also now. And this thing just follows from this statement. Okay, so there is an infrared 4D duality, which looks more complicated, which leads to the mirror symmetry of this theory. So let me summarize the reductionism scheme here. So a lot of simple-looking dualities in a given number of dimensions can be reduced to basic dualities, such as interligator Puyo and cyber dualities. We don't know if these interligator Puyo and cyber are the only basic dualities. So there are many dualities which we cannot reduce to these things, but it remains a question. There is ongoing effort to prove more and more dualities using some basic moves, and it will be interesting to understand whether all Lagrangian dualities in lower dimensions can be understood in terms of some set of very, very basic facts. I grouped here also the construction of lower dimensional dualities using compactifications, because if you start in 4 dimensions with a Lagrangian theory and you compactify to get a 3-dimensional theory, it's again, you have some complicated Lagrangian, more complicated than you want to in 3 dimensions, but you do a 4-dimensional, some simple operation of dimension reduction. Let me next consider something which generalizes all that I have been talking about, and I will call it a big data scheme. So we have a lot of SQFTs in various dimensions. And we discussed various ways to think about these theories and about RG flows interconnecting them. But there is a wide variety of ways to organize our thinking about these dualities. There are a lot of theories, and we can slice these theories in different ways and study interrelations really algorithmically and experimentally, meaning doing theoretically experimentally. I don't know what the proper word would be. But trying to do something bad to these theories in all possible ways and see what comes out of it. And we can look for patterns and try to understand physics from these patterns. So let me give you several examples. So example number 1 is that we can study conformal gauge theories. Okay? Again, like n equals 4 and some other theories that I have mentioned. This is a very small slice of all the possible theories that you can have. But you can study this slice very algorithmically. So you can choose gauge groups and matter content such that all the beta functions will be 0, and you will have a non-trivial conformal manifold, and there is a very well-defined algorithm how to construct such Lagrangian theories. Then you can study interrelations between these different Lagrangian theories, or look for Lagrangian conformal descriptions of some other SQFTs that you can define more abstractly, for example, using a geometric scheme. And here I just show you several examples. So these are 2 theories that have weird names. These are theories which are compactifications of a 2,0 theory on certain surfaces. You can scan all the possible Lagrangians, conformal Lagrangians that you have in 4 dimensions, and you can find several Lagrangians that meet all the criteria to be a cross-dimension dual for these theories. These are very simple, but a bit weird, random-looking quantum field theories. The fact that they are conformal in particular means that all the R charges of fields in this quiver are 2/3, so there are these results. You can start with a random gauge theory in 4 dimensions. For example, a G2 gauge theory with 3 fundamentals and the field in 27-dimensional representation. It's a random theory. The only thing which is nice about it is that it is conformal. And you can ask whether there is another conformal gauge theory which is dual to it, and you can very algorithmically derive such a duality, and you can do other things. So although derivation is very algorithmic, the results lack any structure. Okay? So we obtain data, but we don't know what the structure is. Another thing that you can do, you can start from a collection, your preferred collection of quantum field theories, say in 4 dimensions, and just deform them in all possible ways. You can ask, what happens, what are the infrared fixed points of a given set of theories? Like you study all the possible relevant deformations and look on the results that you obtain. And also here you can find very interesting results. For example, one way to deform a theory or study renormalization group flow is not to consider only conformal Lagrangians, which, as I said, imply that the R charges of all the fields are 2/3, but you allow R charges to be some other values. For example, the next simplest thing is to allow R charges which are 1/3. One of the main kind of surprises, which in retrospect are trivial, is the existence of n equals 3 SQFTs in the landscape of theories in 4 dimensions. These are some strongly coupled SQFTs, and if you open a textbook, you find that there is no way to write a Lagrangian for n equals 3 SQFT, but the caveat is that there is no such way if you insist on the Lagrangian having n equals 3 supersymmetry, okay? Because it immediately becomes n equals 4. However, you can construct a Lagrangian which is only n equal 1, which flows in the infrared to an n equals 3 SQFT. And here is a simple Lagrangian. This triangle here is a trifundamental of 3 SU2 groups, so it's a completely Lagrangian theory. And here is a Lagrangian for E6 Minahan-Nemeshansky theory. There are Lagrangians which were obtained by studying different deformations for various Argyros-Douglas theories, which are complicated, strongly coupled theories in 4 dimensions by Maruyoshi and Song. You can find even infrared duals for n equals 4 super Yang-Mills, maximally supersymmetric Yang-Mills theory in 4 dimensions. Just this observation was made relatively randomly by, again, studying various deformations. If you take 3 Argyres-Douglas theories of certain type, you gauge some symmetry, you can argue that this theory flows to n equals 4 superangles in the infrared. Again, there are many results which you can derive algorithmically, but we don't understand the structure. Here's an example of an experimental kind of result that you can derive, really like you are studying. Maybe you can interpret this as a plot studying some galaxies somewhere, but really these are just A and C anomalies of some theories that you obtain by various deformations. There is this very famous bound due to Hoffman and Maldacena on A and C, so A over C has to be bigger than a half or smaller than 3/2. The bounds are saturated by free fields, by free chiral fields and free vector fields. But if you study renormalization group flows which lead to interacting quantum field theories, you find that the bound seems to be stronger. Okay? So A over C seems to be bigger or equal than 3/5, which would imply actually that this 't Hooft anomaly for interacting theories is non-negative. Okay? I don't know why it is true. This is something we discussed with Nikolai, but we could not prove it and we could not disprove it. So if you can come up with a counterexample, it would be nice, but it seems like a strong statement if it is true. And again, it is just follows from experiments. We don't know if it is true or not. Let me also briefly mention that there are other ways to slice the space of all possible theories. For example, you can study moduli spaces of different theories. There is a lot of effort to try to understand moduli spaces of n equal 2 quantum supersymmetric conformal field theories in 4 dimensions. There is the famous Seiberg-Witten geometry associated to such Coulomb branches, and there is a lot of work mainly by Philippe Argyres and Mario Martone and their collaborators to systematically classify all possible Seiberg-Witten geometries and try to understand what are the field theories corresponding to them. More generally, moduli spaces of theories with more than 2 supersymmetries. So it's not just n equals 4, it's also n equals 3. Theories have been studied extensively also by these people. And there is some interesting relation to mathematics of complex crystallographic groups. So the 2 classifications seem to be related to each other. And here also you can ask whether all of these theories that you can, existence of which you can conjecture by conjecturing existence of certain Coulomb branches, whether they have some kind of a Lagrangian description, some kind of a theory which flows to them. In many cases there is, but in many cases we don't know of such a construction. Higgs branches are more complicated. Again, you can study n equal to 4-dimensional theories for which Higgs branches are a well-defined notion. And it is a fact that many Higgs branches can be realized, the geometries of a Higgs branch of actually theories not just in 4 dimensions but in other dimensions too, can be realized as Coulomb branches of 3-dimensional n equals 4 theories. And this is related to the mirror symmetry that I mentioned before. So instead of studying the higher dimensional Higgs branches, one can try to understand Coulomb branches in 3 dimensions and classify them and classify their properties. And this is a program led by Ami Hanani and his collaborators, and it goes under the name of magnetic quivers, where the magnetic is related to the fact that you need to use mirror symmetry to discuss these Higgs branches. You are really looking at Coulomb branches, but which are related by mirror symmetry to Higgs branches of theories that you are interested in. Tightly related to the notion of Higgs branches, there is a lot of mathematical physics. For example, there is this notion of vertex operator algebras, which is thoroughly discussed by these authors. And there is an intricate relation that I think nobody understands, and between Coulomb branches of n equal 2 theories and Higgs branches of n equal theories, following from this very, very interesting paper, which is already very, very old. So if you study a certain partition function of a 4D theory, of a 4D SQFT, which captures information about the Higgs branch, you can reproduce it by studying physics on the Coulomb branch. And it's related to wall crossing formula. So this is an interesting open problem. in more generality, for n equal 1 theories, there is the moduli space are very complicated. For example, you can study partition functions again, and some of their properties imply certain properties of the physics, such that spontaneous symmetry breaking and various other effects. And again, there is a lot of progress on this front recently. So here is the summary of this big data scheme. Many of the questions discussed here are answered very algorithmically. One can produce a lot of results, really performing some algorithmic computations. However, what is the physical significance of these results, or what are the patterns that we are seeing, is a mystery. Okay? So for example, it seems like the right question for the more novel technologies that we have, such as machine learning. We have a lot of data, a lot of precise data, but we don't understand the patterns. For example, some of these patterns would lead us to the geometric scheme that we have discussed before, but maybe there are other schemes that we can extract from this data which we don't understand, and will teach us about physics in different dimensions. So the discussion that we had till now was centered on Lagrangians. Again, as I said, I am not willing to discuss something which is non-Lagrangian. However, these different schemes, they give us alternative ways to think about theories. And that was one of the original motivations to call certain theories non-Lagrangian. For example, you can define certain theories geometrically, as we have mentioned. You choose a 6-dimensional theory, you choose a geometry on which you compactify. This defines a 4-dimensional theory, whether it has a known Lagrangian or doesn't have a known Lagrangian. There is a theory which exists, and you can ask whether you can compute about this theory anything. Okay, and in many cases, or in some cases, you can use this geometrical understanding to come up with precise computations. An example of that is the famous AGT correspondence, where you can relate S4 partition functions of certain theories to some 2-dimensional CFT correlators. There is a similar relation between superconformal index and topological quantum field theories, and vertex operator algebras are yet another example. So let me tell you a little bit more details about this supersymmetric index computation, and you will see a bit more in Anton's talk. So if you have a 4D theory that you obtain by compactifying certain 6D theory, and when you compactify, you glue this theory by constructing it from building blocks that you obtain from a very particular cutting of the surface and obtaining a very particular 5D gauge theory description, the indices of all theories can be shown to have this form. So there is a geometry encoded in this form. There is this genus and the number of punctures, and there are these special functions which appear here, which can be shown to be related to eigenfunctions of quantum mechanical integrable systems defined by the 6D SQFT and the 5D compactification. For example, in the case of 2,0 theory, this integrable model turns out to be the Ruisenaar-Schneider model. In the case of the E-string that we mentioned, it's another integrable model, which is called the BC-Van Diechen model. And there are other types of models that you can find. So it seems that the classification of the 6-dimensional quantum field theories and their 5D compactification is tightly related to a classification of a sort of integrable models. And here let me mention a historical anecdote. So these eigenfunctions which appear here in certain cases, they are what is called McDonald polynomials, and they have a very interesting history. So they start with Freeman Dyson many, many years ago. In '62, he studied real physics, not toy models. He wanted to understand the statistics of energy levels of complex nuclei. He had to perform certain integral that he couldn't perform, and he conjectured a value for that integral. That value, that conjecture of Wilson was shortly after that proven by Wilson and others. And, it was a cute observation nobody cared about, but some mathematicians are deep thinkers. Again, I don't understand their motivations, but they saw the identity of Dyson and said, why we would not Q-deform it, complicate it a little bit more. And it became a much more complicated identity. MacDonald saw a much deeper structure in this identity, and he associated it to various root systems and developed a whole theory of symmetric polynomials to prove these identities. And these MacDonald polynomials made a full turn to physics, and they started appearing in a lot of supersymmetric quantum field theories in context starting from the 90s, and in particular these indices. So again, I stress this tight relation between supersymmetric quantum field theories and mathematics. You know, all happy families are alike. So, so it's worth reading math sometimes. And a final example here that I will give is that, again, there are other ways to write supersymmetric indices and partition functions using various mathematical objects. For example, you can expand supersymmetric indices in terms of Eisenstein series, and the result is surprisingly simple. And we don't understand, it's again some experimental fact. We don't understand why it is simple. Because it's Eisenstein series, there is some modular properties or quasi-modular properties of these indices, and this is something that will be nice to understand. And I will finish with 2 slides, how this program can go further. So the whole idea of what we have discussed is to start with complicated physics and somehow try to understand the more simple facts about the physics. But we can try to do things the other way around, okay? So we can try to build complicated theories starting from simple ones. And this is how we do things, for example, in condensed matter physics. We can take a lattice, which is just a quantum mechanical system, labeled by some abstract lattice, to which we give a special interpretation, and go to certain limits to construct quantum field theories in higher dimensions. So we can do similar things with CFTs. We can maybe group them in certain ways and take certain limits and try to construct physics in higher dimensions. In condensed matter, this type of theories are usually called wire constructions, so you can couple wires and take these limits. In supersymmetric theories, a canonical example of such a construction is what is called quiver theories. And we can hope that this insight of Anderson will be also relevant in our field. So there is an example of such a construction, of course, going 20 years back. And it goes under the name of deconstruction. So you can make this kind of observations and try to construct certain types of 6-dimensional theories, 2,0 theory, and even little string theories. What is important about this construction is that space-time symmetry is believed only to emerge in certain limit. It is important that many constructions that we have considered had other symmetries, like global symmetries and supersymmetry, emerging in the infrared. But it seems that to consider theories in all numbers of space-time dimensions, we also, in a sense, have to give up space-time symmetries and see them as emergent. So let me finish with this summary slide. So in recent years, we accumulated a lot of data about the space of all SQFTs. There are many structures and patterns that we can see. I think it's fair to say that we understand the space of SQFTs much, much better now than 20 years ago. But with great knowledge comes great sorrow. And I don't know, preparing this slide, I could not, there is something that we are missing. There is a lot of things that we know, but clearly there is something that we are missing. And I hope, studying these questions will lead to some fundamental, better way of understanding QFTs. Thank you.
Thanks a lot for a beautiful overview, David. First question. Thanks. No, because otherwise people cannot hear.
I was wondering how much of this very interesting structure extends to non-supersymmetric theories. And related to that, since you mentioned QCD at the beginning, is there any new insight one can get on QCD, for example?
So at the moment, since anomalies, what we know for non-supersymmetric theories till like 5-6 years ago was only anomalies for usual symmetries. So we could match symmetries and anomalies, and these are not enough to make reliable predictions about the physics in the infrared. Once you go to supersymmetry, you have a large number of other tools which we can rely on. In recent years, there are these generalized symmetries, non-invertible symmetries, and so on that we can also use in non-supersymmetric context. But I think it's fair to say that, there is a huge gap between what we understand for supersymmetric theories, which is a lot, and for non-supersymmetric theories, it's next to nothing. There are some results in 3 dimensions. So in 3 dimensions, people did discuss non-supersymmetric deformations of supersymmetric dualities, and there is evidence for these non-supersymmetric dualities in 3 dimensions. And about QCD, of course, it's a big motivation, but I think it's fair to say that...
Thank you.
Other questions? Maybe I can ask a question. You didn't mention at all string theory.
Yes.
I remember from the good old days that many of these beautiful dualities can be derived from brane intersections.
Yes.
So you just didn't mention it because of lack of time, or
there was an intent not to mention it. So I tried, sorry, it's Eurostrings, so...
Exactly.
So the string theory is in the background of this all, of course. The sheer fact that 6-dimensional SQFTs exist and 5-dimensional SQFTs exist follows from string theory. So string theory is there. For example, I mentioned these 6-dimensional dualities that we don't understand, but we can derive various examples of them. This is what appears here. So I think to derive these dualities, you will need string theory, for example. So these are dualities between 6D SQFTs compactified on certain geometry. So again, the next level of complication will be string theory. So that would have been the next chapter. You have to go to string theory, maybe to understand all of it. But again, this talk was, the task I was given is formal QFT. And we can say that...
but it's good for the young people to know.
Yeah, maybe I'll ask also a general question. So in a sense, in the talk, we see many different relations between different theories. In a sense, we start to map out the ambiguities in our understanding. There's many different things that appear different, but they're the same. Have we understood something really new by the duality, something we didn't really know?
You need to define what you mean by really.
So something which is about a new physical result, which we didn't know before the dualities.
No, I think it's fair to say that, there is nothing new, really new, something that you could not find an example of in other cases. There is one thing that you can say, for example, that, what Seiberg dualities gave us. One thing that they gave us is this understanding that gauge symmetry is not a fundamental symmetry. So in that respect, I think, I cannot really tell you something which is sharp, but these types of understanding of how to view quantum field theories, that gauge symmetries are not fundamental, that to write a Lagrangian, for a CFT that you want, you need to give up symmetries. Symmetries emerge, and this is a fact of life with which we have to live. Of course, it's not a new understanding. It's a very old understanding. But, to construct a Lagrangian, this, I think, was one of the confusions of calling these theories certain theories non-Lagrangian, because we insisted on writing Lagrangians with manifest symmetries. But there are symmetries which emerge, and that is the typical situation. So this is one thing. And I think if we will understand these lattice type of constructions much better, this is maybe the way in which we'll really learn something new.
The question there?
Are there examples of supersymmetric quantum field theories that share the same anomalies, symmetries, and partition functions, but are nonetheless not?
Yes, there are examples. So, a nice example, maybe not all anomalies, but take 2n equals 4 theories with very large gauge group. Okay, the indices of these theories, for example, will agree to very high order. You expand the indices in various parameters. If you only tool you use is just the index, and you don't compare the indices precisely, you just take million first terms in the indices will agree. Okay, so there are examples where more information agrees. So the fact that this protected information agrees is not a proof of a duality. It's just evidence for a conjecture. You need to find more evidence, and yeah. Nothing, even Seiberg duality, is not proven. Maybe some people think that it is a fact of life. I thought definitely when I was younger that it is a fact of life, but it is not proven. So it's a conjecture. You can arrive at this conjecture in many different ways. For example, as I mentioned, you can arrive at Seiberg duality using these geometric constructions as some consistency condition on this construction, but still you are operating in a very limited set of observables, and it might not be true.
A question in the top.
So you were talking about all these different tools we use to do these different conjectures and compare things. Is there anything that you think is so the word tool itself kind of implies to me that they might not be too fundamental. Is there anything that we know is kind of fundamental in the definition of a QFT or so that's always there? We can always compare.
You mean as a tool?
As a tool.
Well,
which is the best
are
tool?
A good tool, but other than that, there is no general thing. Yeah, but also relating to that question, for example, you can ask whether there is a finite amount of information which defines the theory. This is also relating to a talk of Ben a couple of days ago. So anomalies by themselves, they don't define a theory. But is there some finite number of information that you can specify, some invariant not related to a Lagrangian, that you can specify that completely fix a theory? This is a nice question to have in mind. Another question that I didn't mention, I mentioned is theories with emergent symmetries. But in some cases, for example, we can construct Lagrangians for a given CFT, which manifest in the UV only part of the symmetry in the infrared, but always a different part. Like there are different Lagrangians, but you cannot find a Lagrangian which manifests everything. So for example, is there a fundamental obstruction to finding a Lagrangian manifesting certain symmetry? This is another fundamental question that you can try to answer. And I don't even know how to think about it because it's kind of an opposite of anomaly matching. So there are questions here that you can come up with, but...
And maybe if I can ask another question? Okay,
no, I think as a chair I'm going to close it. But yeah, there's a coffee break because we have to keep on schedule. Sorry about that. Let's thank Shlomo for the great talk.